12, 2, 15. Doing the noble gas notation for zirconium the fast way, well, we can look and see that it's going to be something based off of krypton. So zirconium is equal to krypton plus, and then the fast way to do this is to go, oh, okay, well, it fills 1, 2, 3, 4, 5, the 5s, and we don't even have to look up what krypton ends with anymore, because now we just go, oh, okay, 1, 2, 3, 4, 5. This is 5s. So we have a 5s2, and then we know that D is always 1 behind, so 3D1, 3D2. Or I should not make those circles. 3D1, 3D2. I'm sorry, 4D. Jeez Louise. I need a full-time keeper. Okay. 4D2. Okay, because we know that the D's are filling 1 behind. And for the other example we had, which was copper, so up here, copper, we look up and see that copper is going to be based on argon. And again, we don't even have to think, well, what did argon finish filling with? Because we can now just go, okay, so we've got argon plus, let's see, 1, 2, 3. Okay, this is the 4th period. It's filling 4s. 4s is full. 4s, 1, 2. And then D is 1 behind. So that'll be 3D. And then I just say, oh, okay, well, 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9. Done. 3D 9. Much faster, much simpler than what you've done in the past. It's a pretty darn handy shortcut. So, you know, at this point, or if not, and this is copper, at this point, or if not at this point, very, very soon, you can almost automatically look at something and go, oh, well, that ends with a P3. Oh, that ends with an S2. Oh, that would be a, you know, D whatever, okay? So that's what that block arrangement to the periodic table allows you to do. And it makes that process really fast. Why does it matter? Because those electron configurations govern the ions they form, and therefore they govern how they behave. So we actually, I realized when I look at the notes, did not finish talking about the P block, which might have been helpful. So we failed to mention this. I think we sort of glossed over it, but that the P block does have all the nonmetals. It's got all the metalloids. It's really diverse. It's got a bunch of different stuff. And it's got the halogens. Those are really important. You should know the word halogen. Okay? Whoops. Halogen is definitely something you want to be familiar with, because I'll refer to the halogens, and I'll kind of expect that you know that. So the halogens are the group 17 elements: chlorine, bromine, iodine, fluorine, geez Louise. They are the most reactive nonmetals there are. You know, the sort of, I'll call it the bank robber metaphor. They only need 1 electron and they'll do anything to get it. You know, it's dramatic. They are 1 electron shy of a full S&P. So they are super reactive because they've just got 1 they have to get rid of. They get rid of that really easily. So the D block is that center section, that dropped section of the periodic table on the table that we traditionally see on this one. Whoops. And the D block are also called the transition metals. Remember that you start to have those weird overlaps with the S and then it drops back 1 to D. So this is where you start to see that. There are some other weird things that happen with the D block. We'll talk about those in a second. So the sum of the outer S and the D electrons are the group number. The concept of valence electrons gets really strange here. So what have you always learned that valence electrons are? The textbook definition you've known since you were freshmen. Electrons in the uppermost occupied energy level. Yeah. And we've been working with that definition. And valence electrons are the ones that participate in chemical bonding. If we know how many valence electrons it has, we know what kind of ion it will form. Well, in the Ds, it gets weird. Because remember that those Ds are not on the uppermost occupied main energy level, are they? They're one back. So, for instance, you know, we just did copper. And copper was argon 4s2 3d9, right? Those Ds are not on the uppermost occupied main energy level, are they? And yet they participate in bonding. What? What's supposed to happen? The valence electrons participate in bonding. The uppermost occupied main energy level. In the D block, we get some really weird crossovers, and we get, it's called delocalization. Let's just say they're not quite married to their location. They drift around a little bit. So we get things that are in D orbitals that end up doing some weird hybridization with S orbitals, and we get metallic bonding. We'll talk a lot more about it next chapter. But the big thing to know is that the Ds basically function like valence. They're still not called valence, but they function in that way. So the D block are everything you think of, and the D block is what you think of when I say metal. When I say metal, you think of copper and gold and zinc and iron. That's you know, we don't think of sodium and calcium as metals. They're metals, but the D block is what you've always thought of as metals. So all the things you know about metals: good conductors, solids at room temperature, they're hard, they're malleable, they're ductile, they're lustrous, they have shine. But the transition metals are not as they're nowhere near as reactive as the alkali metals and the alkali earth metals. Now, some of them are reactive. Iron, we have lots of iron compounds all around us. If you leave a hunk of pure iron out in the atmosphere, it will react with the water in the air. That's fairly reactive. I mean, it's slow. Aluminum will do the same thing. If anybody has an old aluminum storm door, they get little white pits on them. That's rust, in essence. It's aluminum oxide. It's oxidation of aluminum. Aluminum's not transition, sorry. It's on the edge. Copper oxidizes. Anybody have a copper ring or bracelet ever in their life? The little ones that you got out of the 25-cent machines at the grocery store when you were a kid? They turn things green. They turn things green because copper oxidizes, and actually most of those are an alloy that contains copper, but the copper is what oxidizes. Statue of Liberty. Her skin, her sheeting is made of copper. Not copper colored though. It's green. That's copper rust. That's what copper rust looks like. It's copper oxide. So those are fairly reactive. I mean, they'll react with atmospheric moisture. On the other end of the spectrum in the transition metals, we have things like gold, which is so unreactive they can use it inside the human body. Do you know how many chemicals are going on in the human body at any given moment, at any given location? Tons. You've got acids, you've got, you know, free ions floating around, you've got sodium potassium ions, you've got calcium ions, you've got all this stuff happening. It's a great place for a chemical reaction to occur if it's going to. But some of the transition metals are actually so unreactive they can be used inside the human body and they don't react. Titanium is one. There are people who get titanium joints. You know, gold, there's actually, there are some experiments with gold mesh stents. So where they put basically a mesh support inside an artery, very often done around the heart, around the aorta. A woman I used to work with, her father had a stent inserted and it was gold. So her joke was always, Larry's got a heart of gold. Well, he does now. Get it? Heart, stent, gold, never mind. Okay. So those things are, it's a pretty high standard to be non-reactive enough to be used in the human body. And interestingly enough, humans have been doing that for a long time. What do you think is the earliest use of a transition metal inside the human body? Gold fillings. Gold and silver. Now, of course, they used an alloy of silver and mercury after the age of gold. But gold got a relatively low melting temperature. You know, you could go home and build a little smelter and melt down gold yourself, if you were interested. And it's really super soft. It's easy to manipulate into something like a hole in a tooth. Lead is the other one. We don't use lead in the body. We know better. Mercury, however, alloyed with silver, gives you something with a nice low melting point. We used that in fillings for years. There are some issues with that too, mercury being a neurotoxin and all. But yeah, so a lot of these transition metals do get used inside the body. And we use a lot of these every day. You know, the world around you, look at this room. We are dependent on multiple transition metals in this room right now. Name me one big one. So we've got the structural steel, but the copper, not only the circuitry in all the electronic devices, the phones, the iPads, the Apple TV, the TV, all the wiring that's generating all the stuff in this room that we're using, the electricity, getting the electricity from the point where it's generated to here across the grid, that's all transition metals. So pretty heavy metal economy. The F block. They're the ones we don't... Okay, so the F block and the D block are those ones that typically get stuck underneath the periodic table just for space savings. And they're metals. They're considered metals, though we don't usually even think of them in those terms. They're groups 6 and 7. So they are groups 6 and 7 respectively. They tuck in, and on some periodic tables, I'll show you what I've done. I have sometimes on a periodic table done this to show where those fit in. That they pop in, and if you notice, this is 57, this is 58. This is 71, this is 72. Now, that said, the two that Destiny was reminding me of were lanthanide and actinide, which are elements 57 and 89. On this particular copy of the Wagner, or not Wagner, the Van Braner periodic table, they're shown in the D block, but those are F block elements. I mean, the series are called the lanthanide and actinide series. Lanthanide and actinide are part of that series. Different periodic tables show it different ways, and I don't know why Van Braner chose to show it that way. A lot of them will show sort of a blank spot and then an arrow down, and they'll show lanthanide and actinide in that lower row. It's really clear if you look at what's called the long form periodic table. It's abundantly clear that those are part of the F block. And the long form is probably the best way to do it. 71 and 103 are the ones that probably should actually be D block. So in terms of identity of what block those belong to, lanthanide and actinide, solidly F block. Don't ever think that they're not F block. It's the lanthanide series. Of course, lanthanide's part of it. You know, I don't even remember what those are. 71 and 103, those elements. Don't worry so much about them. They're, well, for one thing, we never talk about them. So the big thing with the lanthanide and actinides, do you notice that these are really large? Not to put too fine a point on it, especially the actinide series, these have masses of like 250 AMUs. These are huge atoms. These are enormous. Some of them that are appearing in parentheses are, let's see, I'm trying to remember. The ones in parentheses, I believe, are averages based on longest lived isotopes. So the lanthanide series, all reactive, about like the alkali earth metals, or alkali metals. So, you know, these things would react with water, they'll react with moisture in the atmosphere. They're not things that we keep around here. Too dangerous. Many of them have radioactive isotopes. Not all of them, but many of them. Not all isotopes of all of them are radioactive. Group, the actinide series, which is the period 7 actinides, those are all radioactive. Every single one of them undergoes nuclear decay. So this is a good time to briefly, because we only have a few minutes, mention radioactive. So when we say that something is radioactive, what does that mean? Did you get this in physical science? Because I know it's in the standards. When I taught physical science, I used to do like 1 day, 1 class period, here's a cheat sheet just so that you've been exposed. Because the standards say that you should get that in that physical science year, but it's really tough to get in. So what does radioactive mean? I mean, we know all the cultural associations with it, like, oh, it's glowing. Okay, no, radioactive things don't glow. Wow, we've got 32-foot earthworms. They were in radioactive soil. No. Radioactivity is nuclear decay. Okay? Something that is nuclear, that is radioactive, undergoes nuclear decay. Okay? So what is nuclear decay? Well, Moser, it's when a nucleus decays. Duh. It means that the nucleus of an atom breaks apart. That's all it means. Is that the nucleus of an atom will spontaneously, on its own, without any prompting, shed pieces. Okay? And there are 3 forms of radioactivity, 3 forms of nuclear decay. We're not going to get into there. There's alpha, beta, and gamma. One of them actually kicks off protons. Let's see. Alpha radiation is a helium nucleus, so it's 2 protons. Beta radiation is an no, it's not an electron. It's a subatomic, it's a sub-subatomic particle. Yeah. It's a particle plus energy. Gamma is just energy. It's a high energy beam. The bigger a nucleus is, the harder it is to hold together. So think about this for a second. What's in a nucleus? What's in a nucleus? What holds a nucleus together? You've got positive charges and neutral. There's no negative charge in the nucleus, though. That'd be a great answer, but they don't exist in the nucleus. And we all know that 2 positive charges repel one another, and those neutral charges, neutrally charged, those uncharged particles, aren't doing anything to help. They're just sitting there. Humph. What the heck holds it? We'll talk tomorrow. Have a wonderful day.